Let's get started. The Spotify API is driving me nuts. I don't know if it's the API or my what I'm using to send the request, but it's driving me bonkers. All right, so let's continue our conversation. Last time we talked about databases, and we didn't quite get to the end, so let's get to the end. Oh, actually, let me queue up the lecture question before I forget, before I have y'all answering about linked lists. Yeah, you get a preview. What's that?
How would you motivate recursion?
How do I motivate it? It's hard. Linked lists too. They're both hard to motivate. I just gotta tough it through. I like recursion, but man, it takes a long time to get an appreciation for it, and 116 students won't.
So I feel like that should have been the answer.
Maybe.
Because the other one was like you're watching them suffer. I'm like technically.
Maybe.
Just technically. More
All
right.
right. Let's finish up these slides from last time. Hi, everyone in chat. Docker Compose. So we use Docker Compose. We've already been using it for just building our app itself. Now we're going to use it to run our database too. Yes. So when I said services before, I said this is a list of services that are going to be created. And each service is a new image and container that's going to be created when you do Docker Compose up. But we only had app. We had one container, so it wasn't super interesting. Now we're going to have two containers, so it does get more interesting. Now, instead of just creating our app, we're going to create a second service. And indentation does matter in YAML files. So anything indented to this level is going to be part of the services object, I guess, key value store. And we're going to create a second service for our database. Yeah.
So I have a question then. Like, is the image mongo, like, does it already have like all the ports configured
Yep.
in the image? Or because like
Yes. Yes. Wait. Yeah. Like 95% sure. Yeah. Yeah, it'll have the port exposed, but it won't expose it to localhost. So from localhost, from your device, you won't be able to access that Mongo container because you can add ports and expose it, but by default you won't. But you will be able to access it from another container. And yeah, where I'm getting hung up is I think it does expose a specific port, the 27017, and then we can access that port only from this app. And I have that 5% uncertainty that maybe containers can just access any ports from each other as long as they're in the same Docker Compose network. I don't feel like that's true, but I'll hedge my bets a little bit there. But we don't have to expose any ports ourselves. I do know that much. Whether this image itself exposes 27017 or not. I would assume that it does and doesn't just let every port be accessed. Please no recursion. Oh, I could add recursion to 312, actually. Maybe I will now, if people like it. So we have two services. Recursion is nice, but really, when you use recursion, like once you get to the point where you understand recursion, excuse me, at least for me, I gained a really strong appreciation for it. But it took years and years and years to get to that point. I forget how far into my PhD. I was in grad school at the time before I really said, holy crap, that's what recursion is doing. That's really cool. But it takes a while to get there. And remember these names. Whatever you name your services, and these are literally whatever you want to name them. Whatever you name your services, you do have to remember those. You have to be consistent with these because that is going to be the host name of that service. I know I've said all this before for those of you who just absorb everything and get it the first time, but this is where it's going to start really mattering, that these are the host names for your services. Because we're going to have multiple containers communicate with each other. And you do have to have multiple containers communicate with each other. That is a requirement of both the homework and the project. You're going to have to run Yeah, be careful with my wording. You're going to have 2 containers, and your app container will have to communicate to a second container to be able to run your database, to be able to access your database. As long as that happens, I don't care about anything else. I don't care how you actually get that database running, but it does have to be 2 containers communicating with each other, because I want you all getting practice with that, with container-to-container communication. It's a very important concept in the modern day. Is that fair to say, I think? But this whole idea of distributed networks of services communicating with each other, whether it's through Docker Compose or not, it's whatever, but you're going to have multiple instances of software I can't say it again without using the word services, but separate services that are communicating with each other to form one single app or one single piece of software. It's just so common these days. Let's get some little bit of practice. And if you're taking the literal course, distributed systems, you're super well aware of this by now. But it's important. So our Mongo actually has a pretty simple setup for this. We got one line here, image Mongo 425, or whatever version you want to use, whatever Mongo version you want to use, that's up to you. You can decide that. I just have 425 in the example because that's the latest one that I used when I made this slide. And I'm using image and not build is important here. So image is going to say, go grab this image off the internet and use that image for this container for this service. And that's it. That's all I'm doing here. This is the same as having a Docker file. I could do build, specify like a Mongo directory, and say, go look in that directory for my Docker file. It's the Docker file that I used to build my Mongo container. And that Docker file could say from Mongo 425. And that would have the same exact effect. But since I don't want to make any other changes, I don't have any configuration that I need to do inside that Docker file, all I want is a Mongo database. Just give me a Mongo database. That's all I need. Since I'm not doing anything else in this Docker file, if I did write one, I'm just going to do image, download this image, and just use it straight up, verbatim. Don't make any modifications to it. And that's it. Whereas for my app, I used build and specified the directory where my Docker file can be found, and then said build an image using that Docker file, and then create a container off of that image. So we got a few different ways of setting things up that we have here. Yeah, sometimes normal is just best. Sometimes not using recursion will make your code more readable, which is usually more valuable than anything else. So yeah, don't get heavy-handed with recursion, even if you love it. I appreciate recursion. I hardly ever use it, just to make that clear. It's just like a neat, nerdy thing, I think. Except in certain applications. Certain things, it's just easier. And that's it. So that's our database container. One line. If you're using MySQL, it's going to be more than that because you have to set up. And if you're using MySQL, I'll let you go out. If I have time, I can show an example of it, but I'll let you go out and find the setup for it. But if you're using MySQL, MySQL does require you to set up an account and a password, and you'll do that through environment variables the same way I'm about to explain right here. I even have it on the slide. Good job, Jesse from the past. You'll need to set up your variables for your username and password, or at the very least, setting your root password using a very specifically named environment variable that the container is going to read on startup, on the first startup. So you will use more environment variables, which you can do right in line, image, MySQL, whatever version you want, and then environment, and then your variables that you want below here. So environment, this is what we'll use to set any environment variables. If you have not used environment variables before, if you've never heard of that, they're effectively variables that are, somebody's going to call me out on this. I'm going to say the wrong thing. Like variables at the OS level is what I was going to say. But I think you can have per user environment variables too. So like per user, but they're still at the OS level. So outside of any running processes, you have a set of variables that are in the environment outside of all your running processes. So your environment variables, there are some programs that are made to read these environment variables, and we can use these for certain configuration. That's what we're going to use it for here. We're going to use this for configuration. So I'm going to set an environment variable named wait underscore hosts in all capitals, and then Mongo colon 27017. Very, very specifically. And then I'm going to update my Docker file with these two lines, which you should just cut and paste. And I'm going to add this /wait and Python app.py. We're going to do this very specifically. And the reason to do this, the big issue, if you ignore this, some students just say, I don't feel like doing that, and they don't. Or they do depends on. They'll read up some Docker documentation, Docker Compose documentation specifically, and find depends on and use that as the solution. So let me tell you what the problem is, why we're doing all this. This is because your database and your app, they're going to be started not necessarily at the same time, but they're going to be started roughly at the same time, at least in an order we're not easily going to be able to predict. They're roughly starting up at the same time. So your app is going through its startup script, and the database is going through its startup script. Now, the database takes a while to initialize. It takes, whether you're using MySQL, MongoDB, Postgres, whatever you're using, it's going to take a while to spin up that database and get it all ready to go. And you'll see this in your Docker output. You'll see a whole bunch of output from the database as it's initializing everything and setting things up. The point is that's going to take a while, at least a matter of seconds. It's going to take a while to start up. Meanwhile, your app is starting up simultaneously. This is happening concurrently. So this got a big startup script to go through, and your app is going to start up without much startup, without much initialization. It's just going to go right into starting the TCP socket server. And what's the first thing, one of the first things that your app is going to do? Connect to the database. Database is still going through its startup script. Tries to connect to the database. It says, database ain't taking connections, crash. Then database finishes its startup script and says, okay, I'm ready for connections. This is the problem we have to solve. We need our app to wait for the database to start and then have our app start. Some of you who want to use depends on, and you can write your code. By the way, you can do stuff in your code to make this, to mitigate the problem here. You can wait until you need the database before you try to connect to it. That's one way to mitigate the risks here. You could have fault tolerance in your code. You can do a lot of stuff in your code. So if you want to do this a different way, by all means, go for it. This is the simplest way that I found. So what some students try to do is use depends on. I like to say this in lecture just because I see it so much in office hours and their code doesn't work. And they're like, well, I found depends on instead of doing the thing you said in lecture. Depends on, you can say this service depends on this service. So don't start this service until this service starts. So Docker Compose will now enforce the order in which your containers start. So it's going to say, hey, you container, database container, this other thing depends on you. So you start first. And it goes, okay, let me start my startup script. Then Docker Compose says, okay, other container started, you can start now. Same problem. Just because this container started doesn't mean it's ready for TCP connections. So this problem that this solution that we have here is going to wait until the database is accepting TCP connections through this wait command. So we're going to run the wait command, which we downloaded through these two lines, or we downloaded through, oops, I don't want to open it. We downloaded through this first line, and then we change its modification so we can execute it in this line, and then we call it, and we wait until this command returns, and then we start our app. What this command will do is read the wait host environment variable, and when this host and port is accepting TCP connections, it will continuously try to open a TCP connection. Once that TCP connection, the three-way handshake, is successful, then it says, okay, we're good to go, and then it exits, and then we go on to our app. So this solution makes sure that that container is accepting TCP connections. So it's waiting, okay, try to TCP, doesn't work, waits. Tries the TCP, okay. Done with the startup script, tries the TCP, oh, hey, we got a TCP connection through handshake's good, we're good, and then your app starts. So this is an effective solution that makes sure your database is running without any crashing, any of that stuff. This is a host name, so it has to match exactly your service. That's the first time where that's going to be very important. And shout out to this person I don't know, but UFO Scout on GitHub created this kind of workaround hacky thing to make this work and release this code for all of us to use, put it on GitHub. So, I don't know, give them a like or something on their GitHub repo, which you can do. Some people call GitHub a social media site. They're not wrong. I feel weird saying that it is, but it is. So this is my solution. If you want to use a different one, this is the best solution I found that's out there. UFO Scout does have a PR. Last I checked, it's still pending, but a PR to actually add this feature to Docker Compose, which would be nice. But until then, well, we'll use it the workaround way. And then you run Docker Compose up, --build, --force recreate, and it creates both containers. So the next place where the service name matters, the service name is going to be the host name, is when you, and I just realized my slides are going to be a little wrong in the next slide. When you're connecting to your Mongo client, this is what we did last time. We connected using localhost, and that's what all the documentation that you see is going to do. It's going to connect with localhost. At least any intro documentation is going to use localhost. So you're going to connect with localhost, but once you run this through Docker Compose, you have to use the host name of your service. So we're changing that to Mongo or whatever name you used right here to connect to that database. So that's the second and last time where that host name is going to matter for your database. And it'll come up again in homework 4 territory when we start using Nginx. So make sure you're changing this. It's one of them things that you just have to remember to do. If you're doing local testing, it's a lot quicker and easier if you download the data, either download a database and run it locally, or use Docker to run your database without your app and then connect to localhost. I mentioned this last time. It makes things a little easier to work with. For that, I do believe you'd have to map the port. Yeah, you'd have to map it to a local port if you want to do localhost like that. But what's really important about that is when you submit your homework, make sure you have this configuration. Make sure you're testing to make sure it works in Docker Compose, even if you're testing without Docker, because it's faster. We like faster debug cycles. I don't debug my apps with Docker Compose unless certain situations, it's just a really quick thing that I got to do. But I'll set up my dev environment to not use Docker and then go to deploy, make sure it works with Docker, and then deploy. So when you go to submit your homework, make sure you have the right configuration. I've seen too many students, not a ton, but 1 or 2 each semester, who will submit with the wrong configuration, and they don't test their app, they don't follow the recommended, download your zip from Autolab and actually test it the way that we're going to test it. They don't catch that, and they lose a lot of points. I don't like to see it, but at the same time, I'm not giving the points back. Like, you gotta not make that mistake. So make sure that you have the right configuration when you submit. It's easy to forget unless you're actually testing your stuff after you submit. That's why I have that big warning in every homework document. It's strongly recommended. Test your app this way. This is the first one that's going to catch, hopefully nobody, but has caught some students in the past. Just make sure you have the right configuration. The TAs aren't expected. I don't expect the TAs to debug your app. If it doesn't work, they're not going to fix your app. They're just going to say, well, it didn't work. Move on to the next assignment. Bless you. Bless you. So whatever you name your service is the host name. Hopefully I said that enough times. And just to prove this point home, drive this point home, and this is my slide that's messed up. I should change it here as well. This needs to also be my super cool database. But this is whatever you want to name your service. I name it Mongo just because, I don't know, that's made sense. It's a Mongo database. But if you want to call this whatever you want, just make sure you're consistent across these. I'll have students who change the service name but don't change this name. I want to make this clear. You got to change it in all 3 places. Even I forgot, so yeah. But it's easy to forget. But this wouldn't run, and then I'd catch it. I just changed it in the slide. But you would have to change it here as well. So wait host works as well. So you can name it whatever you want. You just got to be consistent. So if you change it in one place, make sure you change it in all 3 places. I'm going to rip through templates kind of quick, I think, because I want to get to authentication. But we have this problem where sometimes we want to return custom HTML to a user based on whatever their specific request was. For homeworks 1 and 2, I structured them in a way that avoids this, so we don't have to worry about it until homework 3, and you'll have to worry about this on the project, depending on how you structure your project, actually. But there are times where we want to serve different HTML to different users based on specific state, depending on the user. And to do that, what we can use is HTML templates, where we store incomplete HTML files on our server and then replace certain pieces of information server side before we send that content. So we say that we're going to take an HTML template, render it with a specific set of data, and then send it to the user. So this would be an example of an HTML template. It's mostly a page. It's not very interesting, but I have a few placeholders. And for the slides, I'm using handlebar syntax. That's just kind of the HTML template engine that I stuck with whenever I need one. Handlebars is a library. You're free to use it on your projects, but not on your homeworks, notably. Your homeworks, I would expect you to do your own templating. But I'm using placeholders here to say there's information that should go here. And then when I have a request for this content, I can fill in whatever information I want in these placeholders to be able to use the same HTML template to render different pages with different content. So I get a request, I read the HTML file, I read it as a string or convert it to a string, and then I do find and replace with each of the values that I want to replace, and get the content that I want in there. We can do loops. If you use handlebars or any other template engine, I shouldn't say any other, but they should all have this anyway. We can have loops. If I have content that needs to be rendered for each element of a data structure, I can have placeholders that indicate the start and end of a loop, and then placeholders inside the content of the loop that needs to be rendered for each element of that data structure. And conditionals. And conditionals as well. Look for your tags, if, some conditional, and then figure out how you want to resolve that conditional. You can even have else and some way to indicate the end of the else block. These are typically things you're going to have in your HTML template engines. So for your project especially, if you want dynamic HTML that's rendered server-side, HTML templates is the thing to look for. Since you don't have to use those on homework 2, I'm kind of ripping through that. And when it comes more relevant, hopefully there are questions and I can address them, or I remember to get them in the slides in more detail. But let's get on with what today's lecture is actually about. Authentication. And these slides will, 5_2 at the old one. I have to refresh. 2_4. These slides will certainly spill over into Wednesday, but Wednesday slides is like 10 slides. So we have some room to play with. I don't want to rip through this too quick. All right. We've all heard of user accounts, right? So we used everything we've done is just not static, but everything that's served to our users is the same for every single user, and that's not how we experience the internet. We have user accounts, you log in, you see content specific to you. It's typically what we want for most sites that we go to. Not all, but you want to get your specific news feed and, bless you, posts from your friends, whatever. So we want to log in and send something different to all users. The only thing that we did so far was the visit counting cookie. Even if you've done up to Objective 1 on Homework 2, which, by the way, you can do Objective 1 right now, none stopping you from Objective 1. Objective 2, we'll talk about today and Wednesday. After Wednesday, you'll be able to do Objective 2. And then it's, this Friday. Yeah, this Friday we'll do Objective 3, and then next Wednesday is the application objective, with next Monday kind of filling in some gaps there. I don't know. I went into too much explanation there. But anyway, you can do Objective 1, but it's going to be unauthenticated chat, which means everybody sees the same information. Not really what we necessarily want. So let's add features that need our users to be authenticated. For this, it happens in 2 steps, registration and authentication. Registration, you send a username and password, sometimes email address, usually just email and password, or email and password or username and password to create an account. You've all created tons of accounts before. I don't have to dwell on that. Then authentication, you send the same username and password to that site, and they say, as long as the password matches with that username, they're going to say, yep, you are who you say you are, and then you're authenticated. So registration and authentication. Once we get to tokens, authentication tokens on Wednesday, it'll be registration and login. But technically today we're only talking authentication. We can authenticate a user, but they can't log in and create a session yet until we have authentication tokens. So a little bit of nuance there, but it's common to verify an email these days. The reason for this is largely to limit bots. Bots will bombard your server if they have any inclination to, if they have any desire to. They'll bombard your server with all kinds of accounts, but they won't be able to verify email addresses, at least not easily. They won't be able to verify email addresses easily. So that stops a lot of bots in their track, and sometimes you have the CAPTCHAs too, of course. That's all bot prevention. That's why we have to verify our emails these days, mostly to prevent bots. Okay, so let's talk about how we're going to authenticate. On the server, somebody registers an account, we get a username, we get a password, we have to store this username and password in a database, and then when somebody wants to authenticate, they send a username and password, we get the username and password out of the database, or we get the password for that username rather, and if the passwords match, we say, yes, you are who you say you are. Generally, that's how it works. And the actual details of that, that is what it is. There's not much magical there. We've already talked about databases. You know how to get information out of a post request. You can do that. You can do authentication, right now. I don't have to say anything more about it, right? The big thing when it comes to authentication that we must care about is how we store those passwords. That's most of the conversation that I want to have about authentication. How are we going to store those passwords? So we have this situation where we have a database full of passwords, right? It's a pretty lucrative target for attackers. If somebody gets access to that, maybe they have a SQL injection attack that you were vulnerable to, or maybe it's just our sysadmin. Maybe the sysadmin goes rogue. Maybe some dev who you gave database access to, that you gave production database access to, maybe they go rogue. Maybe they steal all those passwords and start blackmailing their ex-girlfriend or something. We don't want that. We don't want anybody to be able to read these passwords. So this will be the first of many times I'll say this. Never, never, ever, ever store your passwords in plain text. We do not store passwords in plain text. This is the biggest thing to know when you're building authentication. Never store your passwords in plain text. And just in case I don't, we got 20 minutes, I'll probably get there. But just in case I don't get there, we're going to store salted hashes of these passwords. Salted hashes of these passwords. Never store passwords as plain text, ever, ever, ever. What we want out of our password storage is that not even those admins can tell what those passwords are. If you've ever been in a situation, which you really don't have to anymore, there's password reset links all over everything now. There didn't used to be. And if you lost your password, you'd call up the admin and be like, can you just tell me my password? And they'd say, no. You'd be like, come on, man, just tell me my password. No, they actually can't. They do not know your password. They can't give you your password. And that's the way we like it. We don't want anybody knowing your password. Not the devs, not the CEO, not the admins, not anyone on IT. Nobody can read your password. Ideally, that's the goal. We're not perfect. It's not actually going to happen that way. But we're going to do the best we can. Nobody can read your stored passwords. We do get that. But if they put in some software, some code that can view the login process, your passwords are exposed at a certain point in that login process. But your stored databases, they shouldn't be able to recover those. So what we're going to do is store hashes of those passwords. A hash function, we're going to use a hash function, which you've all heard about at least at some point, at least in 250 when you built hash tables. A hash function is a function with certain properties. This is a very vague description of a hash function, but for our purposes, I'm fine with it. Typically, that property, the hash function is going to be a function where the output has some certain property, usually fixed length. We want fixed length. Like for our hash tables, we have some max index of the hash table. We want a value of 0 to that max index. That's what we want our hash function to return. Hash functions are super important. They're great. We love them. A hash function itself is not necessarily used for security. That hash function you use for your hash tables isn't going to add any level of security to anything, unless it does by accident. It's not going to add security. When we're talking about hashing passwords, don't just pull out any old hash function and just store some hash of your password. Store a cryptographic hash of the password. You need a cryptographic hash function, which I know I'm making this distinction right now, but for the rest of the lecture, I'm just going to say hash function, and I'm going to mean cryptographic hash function when I say just hash function, because cryptographic is a long word, and I don't feel like saying it 100 times. So a cryptographic hash function is a hash function that's meant to be a one-way function. Not all hash functions are meant to be one-way. Some of them can be reversed. So a cryptographic hash function is going to take our plain text passwords, we're going to hash them, and get some randomish garbage out the other side, and then that's what we're going to store. We're going to salt them first by the end of this, but that's what we're going to store in the database. And since it's a one-way function, you can't, I'll say can't, shouldn't be able to, take this and go back to this. You can't reverse a hash function. That's why it's a one-way function. You can't reverse it. But it's very easy to hash a value. So it should be very quick to hash because we got to hash a lot of things, very often. But it should be next to, at least, impossible to take this and compute the original plain text that created that hash. I'm going to talk about SHA-256. We're going to store SHA-256 hashes of passwords, and then not even the admins are going to be able to tell what those passwords are. SHA-256 does a lot of bit-level stuff that I always blank on the specific details, but it does a lot of calculations, and I believe just runs through this logic multiple times. Since it's all bitwise operations, it's very fast to compute, very, very efficient to compute one of these hashes. But going backwards, you just can't jam the output back into this and get back to the input. It just doesn't work for magical reasons. I don't know. I don't remember. Just because you store a hash doesn't mean you're secure. This is one of my pet peeves. For a lot of reasons. This is surprisingly common. I've seen this in published peer-reviewed research, and it's one of my pet peeves because my work would be compared to theirs and been like, well, they got way more security than you. And I looked at it, and it's like, they're like, we hashed it. Don't worry, bro. It's cool. Like, we hashed it. Just because you hash something doesn't mean it's secure. So we are going to hash our passwords, but that's not the end of the story. That doesn't mean it's secure. So what if I have a database that stores your answers, all of your answers, to a yes or no question? If you say yes, I hash yes, I store it in my database. If you say no, I hash no and store it in the database. It's going to take you 2 seconds to figure out who said yes and who said no. Once you get one known value, you'll look up your answer. You know what you answered. Now you know everybody's answer. It's hashed, but it's not secure. Just because you hash doesn't mean you're secure. So, and I do have it. So a brute force attack, so you can attack these hashes. Our brute force attack, you can't go from the hash and compute, and I was careful to say the word compute. You can't go from the hash and compute the plain text that generated it, but guess what you can do? Go from the plain text and compute the hash. That's very fast. That's very efficient. That's what it's made to do. The hash function is made to be fast, going in that direction, in the one-way direction. So you just take a whole bunch of guesses. I think the password's one of these million guesses. You hash them all until you find one that matches the hash that you're stored, that you're trying to crack. That's the hash. This is a brute force attack. In general, you just try every possible input string until the output matches the hash that you're trying to crack. And then once it does match, you know what the input was. You know what that password is. So if somebody has a weak password, you just try a bunch of common passwords and you're going to break that password. You're going to crack that hash and know that password, even though it was hashed. This is why, even though we're storing salted hashes of passwords, there are still password requirements. Every site, it seems to always be the same thing. At least one lowercase, one uppercase, one number, one special character, at least 8 characters, which is actually a pretty weak criteria. But if you go beyond that, you start losing users because they don't even want to go through the registration process. But if you just follow the minimum criteria, it's actually a really weak password. I'll be able to do demos. I'll have time to do demos on Wednesday and show you exactly how weak and why that's weak. Just make your passwords. The short answer to that, the TLDR, spoilers, and everything, just at least go to 12 characters. It's actually enough to be really secure as long as your password is random. And the way we measure how strong a password is with a measure called entropy. So we're going to measure the entropy of a password, not always passwords, but in this context. The entropy of a password is the maximum number of guesses somebody would have to take to guarantee that they got your password. So if they know certain properties about your password, say they know that you have a one single character password and you're only using lowercase letters, in 26 guesses, they're going to get your password. At worst case, it's the last guess that they had. If you have 2 lowercase letters, it starts to grow pretty quick, literally exponentially, and they got 676 guesses to crack that thing. If you just throw in uppercase and lowercase letters in there instead of just uppercase, it grows pretty quick, 2704. Still a tiny, tiny number, and obviously you would expect a 2-character password to be completely broken, completely terrible. But these numbers do get big really fast. So to mitigate that, to make these a little more usable, we usually talk about bits of entropy, which is the log base 2 of the number of guesses. That's our bits of entropy. And that's the measure we like to use because the numbers stay small. Log is, as you should all know, be well familiar with now, is a very slow-growing function. So it keeps the numbers in a reasonable range. And we say at least 80 bits of entropy is a general rule of thumb around security that if you have 80 bits of entropy, you're good. You're secure. You're feeling good about things. So our goal is 80 bits of entropy to feel secure about our passwords. And we can run some numbers, and I intend to on Wednesday, of once you have a completely random password, uppercase, lowercase, numbers, special characters, once you have a mix of all of those and it's 8 characters long, you don't get up to 80 bits of entropy. So you can make it like 12. You can get your bits up. I believe 12 is the threshold. From 11 to 12, you cross that 80-bit threshold. And you can get a secure password if your password is purely random, which it's not going to be. Unless you're using a password manager, I do recommend password managers that will generate purely random passwords, and you can just crank the length up to 30 if you want, and actually have secure passwords, unless somebody breaks into your password manager, of course. But we need, even with the password manager, we need at least one password that we remember. We like to come up with passwords that we'll remember. Because if we can't remember them, how are we going to get into our sites? And attackers take advantage of this. They don't do a brute force attack and try every possible password ever, every possible combination of legal characters. They're going to use what's called a dictionary attack, which starts with our tendencies. First they're going to look up top 1,000 most commonly used passwords list. Those are the first 1,000 guesses that they're going to use. Then they're going to start using common substitutions. We need a special character. Well, I'm going to replace the A in password with the @ symbol. That'll show them. I'm going to replace the O in password with a 0. Now I got all my criteria met, and then I'll capitalize the P. That'll get my criteria. Well, that's going to be coded in the dictionary attack to make all these common substitutions. They're going to, as the name implies, look up the dictionary. Once their top 1,000 most commonly used passwords list is exhausted and they haven't cracked your password yet, they start going to literal words and using all the substitutions and just trying everything that's a common thing that a human might do to try to remember their password and take advantage of those patterns to significantly reduce the search space. So the entropy arguments only works if you have a purely random password. If you have 8 characters, one of each of the 4 things, and it's something that you can easily remember, a dictionary attack is going to tear that password to shreds. If they get a hold of your hash, they basically have your password. It goes further than that. Ooh, actually, I'm gonna get to the salts, ain't I? For some reason, every semester I get to this lecture and I don't get to salting. I was really worried since we had residual slides from last time. So it goes further than that with rainbow tables. So one, make strong passwords, bless you, and force your users. Users are going to make the weakest passwords. Force your users to have strong passwords. That's why that's a thing on the internet, even though the 8-character limit is too small. But no one would use the internet if we didn't. But it goes further than that. Rainbow tables, instead of somebody attacking one hash, so the scenario I gave was they go to a database. Oh, I worded that wrong already. They go to a database, they get your hash, or anyone's hash. They can actually attack every hash simultaneously. They take a guess, hash it, and then look up, okay, did that hash match anybody's password, and attack everybody all at once. But even further than that are rainbow tables. So with rainbow tables, instead of cracking a hash when you get the hash, you get a hash or a database full of hashes, and then you start trying to crack them. The way rainbow tables work is they'll pre-generate these things called, you guessed it, rainbow tables. They pre-generate these rainbow tables which store chains of hashes. What they do is start with a guess of a potentially valid password that meets the criteria, hashes it, then applies a function to that hash that turns it into another valid guess. Some function that, because your hashes are going to be like 256 bits. I guess I was going to say I forgot, but it's right in the name. If they're using SHA-256. And turn that into an actual valid guess, usually a shorter string. That's going to be another valid guess. Hash it, apply the function, turn it into another guess, hash that, and do that, say, 1 trillion times, 1 billion times, I don't know, a bunch of times. And then what they do is store the first guess in the last hash, throw everything in the middle away, and just store those 2 things. Now that what they effectively have is a chain of guesses containing, I'll stick with 1 million, that contains 1 million guesses if they did that 1 million times, but they only have to store 2 values. So it's very space efficient to store lots of guesses in just 2 values. And then they do this millions, billions, trillions of times. These rainbow tables can be gigabytes large when each chain is just 2 values and you have gigabytes of data. That's lots of chains. That's lots and lots and lots of guesses. Lots of guesses encoded in this rainbow table. Now you have a hash that you want to crack. What you do is you take that hash and check if it matches any of the end hashes in any of your chains. If it doesn't, you apply the function to turn it into a guess, hash the function, check if that matches any of the endpoints of any of your chains. Keep doing that at most 1 million times in this example if your chains are 1 million long, at most 1 million times before that guess gets to one of those endpoints. And if it doesn't, I guess the rainbow table's broken. You want to encode every possible guess in these things. And once it matches an endpoint, you know what chain that password is in, you go to the beginning of that chain and start going through the process until you find that hash, and then you back up one step. That's the password. Now you crack that password. So now, instead of waiting till you have a password to throw an attack at it, you pre-compute using tons of time, however much time you want, beforehand, and then when you get your database compromised, you get a whole bunch of hashes, you throw those hashes at your rainbow tables and just destroy those hashes. You crack them, very, very quickly. But not our hashes, because we're going to salt them. If you salt your hashes, which is when we take a password, somebody registers their account, we got their password, we're going to generate a large random value that's going to be the salt. We're going to append that salt to the password and then hash it. And then we're going to store that hash and the salt in the database. So the salt is going to be stored in plain text. Any attacker who attacks this database gets to know what the salt is, and they can still launch their dictionary attacks, they can still launch their brute force attacks, but their rainbow tables are completely useless because their rainbow tables are built off this function that generates these supposedly valid guesses, but almost none of those valid guesses are going to have that salt as their either prepended or appended, whatever you're doing, as their value. It's not going to have that salt in there. So these rainbow tables are useless now because we all know to salt our hashes now.